welcome to the OneClass channel. My name is Fejiro. For those of you that don't know me, I am an honors Bachelor of Science graduate, and I'm currently working towards getting into medical school. Today we'll be going over some commonly asked questions, specifically in chemistry, at both the high school and college level. If you need some more help or you just wanted some more insights and one-on-one work, you can definitely check in the links in the description below. Okay? And with that, I just want to thank you again for joining me this session, and we're going to kick it off right away into our new session here, starting with question 1. Okay. So we have, what is the difference between electron pair geometry and molecular geometry? So, with this type of question, okay, you can kind of hint at what they're getting at based on their name, but the way I like to remember it is that electron pair geometry is not specific to type of electron. Type of bond slash pair. Okay, electron pair geometry, the goal is simply to count out how many connections the element has actually. So for example, if we had this perfect example, ammonia, right? So we're going to do ammonia, so that's NH3. If you drew out its molecular structure, it'll look kind of like this. Okay, so in terms of the electron pair geometry, okay, this is what we have, right? So we're going to count out how many electron pairs that nitrogen specifically has, okay, because we always want to do it from the central atom. We have 1, 2, 3, 4, okay. So the electron pair geometry is literally just based on how many types of things attached to the nitrogen. In this case, the electron pair geometry will be based on 4 4 in terms of the electron number. Okay, that is like not electron number, but 4 in regards to the things attached to nitrogen. So it has 4 things attached. Okay, and because of that, the electron pair geometry is just known as tetrahedral. Okay, because it's when you look at it in terms of the actual 3D structure, this is what you have, a tetrahedral structure. Now, molecular geometry, okay, is specific, is not and is specific to type of bond slash pair. Okay, what does that mean? Same thing, we're looking at ammonia still. Okay, it's no longer just 4 things attached. We now have specifically 3 bonds, because they don't really specify what type of bonds. So 3 bonds and 1 lone pair. Okay, so now it's slightly different from just the 4 things attached, just the 4 electron pairs that it has. Okay, so now because of that, it is still a type of tetrahedral, but it's a specific type. So if we actually look at our Vesper theory sheet here, tetrahedral, exactly, that's our electron geometry. and then what they call the Vesper class, as you can see up here. Sorry. And that would be this one specifically here, because it has one lone pair. So this type of tetrahedral is trigonal pyramidal. Okay, so this is how this sheet is actually explaining. The electron pair geometry is just determined by its hybridization. So as you can see here, nitrogen, nitrogen in NH3 is sp3 hybridized. How do we know? Because as we said, we have 1, 2, 3, 4. So there's an S shell, and then the 3p shells fall after, because every shell is filled in by 2 electrons. So we have the S, we can literally select any of them to qualify as the S shell, and then 3 more shells, which is why we have P3. Okay, so this is just an example. If we had even like carbon dioxide, for example, okay, this would actually refer to as an sp hybridization. Why? Because only 2 bonds. It usually only counts by the bonds, not specifically by the electrons. So like for every bond, it just assumes that there's like 1 electron there. Okay, and I put that in quotations because I'm sure there's a better way to explain it, but the point you have to memorize is that you count starting from S. So S would be considered like your first, and then you add, kind of like following your electron configuration, you add a P for every other bond. And let's say we had one of those compounds like sulfur, we're gonna have like, other things attached to it. I think it's like phosphorus that does something like this, one of those two. But point being is that when you have something like this, now this one will be considered 1, 2, 3, 4, 5. So it'd be S, P, and then P2, P3. So now we have 4, and then we go into our D shell. This would be sp3d hybridized for that sulfur. Okay, but the point being though is that that's what the electron pair geometry is based on. It's not specific to the type of bond it has, it's just based on its hybridization. Now molecular geometry now goes into specifically what these hybridizations consist of, depending on the breakdown, whether it has 1 lone pair, 1 lone pair, 2 lone pairs, or however many of the lone pairs, the shape is greatly affected by that. Okay, so exactly, that's what we have here in terms of the lone pair. The best way I can explain it between electron pair geometry and molecular geometry is that molecular geometry is like a square, and electron geometry is like a rectangle in terms of the definitions of a rectangle. Okay, so as you know, a rectangle has just 4 90-degree angles, but a square has 4 90-degree angles, okay, and all the sides are the same, right? So with that being said, every square is a rectangle, but not every rectangle is a square. I'm sure you've heard something like that before. It's kind of like this, where it's like every molecular geometry, like the molecular, when you get more specific, is part of that original electron pair geometry, but as you notice, it doesn't always translate back. So for example, if we had like linear, where you like carbon dioxide, for example, that's a linear electron pair geometry. When you get into the more specific name, the molecular geometry is actually the same, because there's no other choice. There's no lone pairs to fit in when there's only 2 bonds. But exactly, as you see as you go through, when you have electron geometry of trigonal planar, as soon as you include a lone pair, it becomes a different shape. It's now bent. And you notice every time when you get to the next electron geometry, only when there's no lone pairs does the name stay. In fact, when we go back down, you see, no lone pairs, 5-0 lone pairs, the name stays. As soon as you add lone pairs, the name starts changing. Okay, same thing here as well. No lone pairs, so the name stays the same. But now all these square pyramidal, square planar, T-shaped are all types of octahedral electron geometries, but because they have different molecular geometries, their name changes because it's a different shape now, as you can see from these diagrams here. Okay? So, with that, let's see. The main difference, as I said, is consideration of lone pairs. Exactly. When they actually look at the type of bond slash pairs. Okay? If the molecule has no one pairs, all electrons are bonded. The electron pair geometry and molecular geometry are the same. That is a key part that we just described. But as soon as you start throwing in electrons, the shape changes drastically. Because exactly, like these lone pairs, they kind of push everything to the side, and it typically ruins the shape it was going for without lone pairs. But yeah, so the summary being is that if you want to understand just based on the hybridization, you're looking at the electron pair geometry, and that one's just face value, how many things are attached to it. And the molecular geometry is now when you have to question, okay, of those things attached to it, which ones are actual bonds and which ones are actual like lone pairs. Okay, this is correct. And now let's move on to question 2. Calculate the mass of silver chloride formed. Okay, and concentration of silver ion, so leftover silver ion in solution when AgNO3 is added to 50 mils of 1.0 times 10 to the negative 2 molarity of NaCl solution. And it specifically says assume there's no volume change. So like when you drop your, I guess, solid of silver nitrite, they're assuming that there's no like volume change for you to, so you're still at the 50 mils for your total volume. Okay, so now with that being said, let's actually write down the full equation first, because we want to know actually what's happening in this solution. So we have AgNO3 plus AgCl, oops, wrong one, plus N, so salt, a salt solution, NaCl, okay, and that would be NaNO3 plus AgCl. Oops, this will be solid. Well, actually, it'll be more aqueous because as soon as you put it in, it does change, as in it does dissolve. And the only real solid here is this AgCl solid. Now you're probably wondering why I even put this type of arrow, because if you haven't learned this yet, Le Chatelier's principle applies to literally almost anything, where if you change the amount or the concentration or the temperature or the pressure, things like that, that's for gases. Point being that the equation can shift left or right, especially when you're dealing with precipitate, just because like things like silver chloride, if they're forming precipitate, like turning to a solid, that means their KSP value, their what's it called, ionization, or their dissolution rate, like where they actually dissolve into the system, is low, but it's not impossible, if that makes sense. As in, you can force, if you do certain things, you can force the equation more to a certain side. Like let's say if I kept taking out, it's just a quick note, because I don't want you to ever really think, unless there's specific scenarios where it is just a solid arrow, but always be, in my opinion, be putting this type of arrow in any of your equations, because you really want to understand that these equations aren't just like one way. It can always be most of the time turned back. An example of things that are kind of one way are like combustion, where like you're putting in energy and you're forming CO2 and H2O. Naturally speaking, there's no way to go back once you've combusted the material. But for this, when solutions are being dissolved, solids are being formed, there are ways for you to manipulate it to where you can go back and forth type of thing. Okay, so that's why I usually err on the side of putting that type of I guess equal sign, or going to the next part. Solubility, there we go, solubility, SKSP. So the KSP for HCl is quite low, like a very small number, hence why it doesn't dissolve in water. So aside from that, let's actually go back to the question. So we have the information is that's 10 grams, okay, of AgClNO3, okay. And how much NaCl we have? We have 1.0 times 10 to the negative 2 in 50 mils, okay. And they want to know how much of the solid is formed. So for any of us to do any calculations, we have to convert first into moles. Okay, luckily for us, the equation is 1-to-1 for everything. So after we convert to moles, is relatively straightforward. But that's the first thing we're going to have to do. So to convert to moles, we first need to know the molar mass of silver chloride and salt. Salt, not so much actually, just a silver chloride, because silver chloride is the one that's in grams right now. We want to get it to moles. And I'll show you why we don't need to do that for salt, and I'll show you why later actually. So AgNO3, 1 silver, 1 nitrogen, 3 oxygen, okay, that's 15.999, this is 14.007, and now this is 3 times that is 47.997, I think 15.999 times 3, yep, and silver is 107.87 plus 14.007. Oops. 0.87. We add them all together, we get 169.874. So that is the molar mass for silver chloride. They want to convert that silver chloride from moles to, from mass grams to moles. So what we do is we'd have 10, sorry, that's bothering me. So that's 10 grams, okay. And then because we want to get rid of grams, we put the 169.874 in the denominator. So now these two cancel out. Is 1 mole of silver chloride, silver nitrite. Okay, so silver nitrate, sorry, nitrite's something else. That's silver nitrate. So 10 divided by that, we get 0.058. We can technically keep going. It's 588, so it's 589, and this would be the 3 significant digits since we started out with 3 for the 10.0. So now we know that it's 0.0589 moles. Okay, so now for sodium chloride, salt, to get the moles, actually, we know that to get molarity, right, it's moles over volume. So if we rearrange this, actually, to get the moles, it would equal to molarity times volume. So if we did that, actually, we have 1.0, we have 50 mils, right? And we just want to get the the moles, right? So we have 1.0 times 10 to the negative 2 moles per liter, but that is 50 milliliters. So actually what we would have to do then to make sure we cancel out milliliters, okay, is that we have 1,000 milliliters equals to 1 liter. So here the liters cancel, the milliliters cancel, and all we're left with is moles. So let's quickly do that. That's 50 times 1.0 to negative 10 to negative 2 divided by 1,000. Okay, so we have, wow, that's a very small amount. We have 0.0005 moles. So that's what we have here, 0.0005 moles. Okay, so now since it's a 1-to-1 ratio, right, we have to figure out which is the limiting reagent, and that one is just done by, you want to see of these ones here which is the one that's the least, as in terms of when it comes to the ratios. So AgNO3 and NaCl, that's 1-to-1 ratio, but that's clearly not the case here. So we can pick any of them just to divide by. So if I want to do the 0.58, it's 0.0589 divided by 0.0005, we actually have right now 117, well 118 about when you round it to 1 ratio. So this is clearly in excess. The silver nitrate is clearly in excess, so we have to use it based on the sodium chloride, meaning that we're only going to get, because since everything is 1-to-1, we're only going to get 0.0005 of silver nitrate and 0.0005 of silver chloride in terms of the moles. So yes, it's quite limiting actually. So just to make sure that we do have the right information here, yep, 10 times 1 times 10 to the negative 2, 50 mils of it. So now that we've done that, it's asking us to calculate the mass of silver chloride formed. So now we know the amount of moles that silver chloride formed. We need to know now the mass. So for that, you need to know the actual, again, molar mass of this compound. So we have 1 silver, 107.8, 0.87, and 1 chloride, which is 35.45. 107.87, 35.45, add them together, 107.87 plus 35.45. Okay, and we get 143.32 grams per mole. So now we factor that in using that 0.05. Okay, so 0.0005 moles of silver chloride times, we want to be able to get from moles, so we have 143.32 grams at the top per mole of silver chloride. These two cancel out, so we're just multiplying that by 0.0005. So in total, the amount of grams produced of silver chloride is actually quite small, but this would be our answer. Well, one of our answers, 0. And we want to check with the significant digits. It looks like most of the things we're working with, it looks like it's 2, except for the 10, but we're just going to leave it 2 significant digits. So 0.072 grams. That right there is the molar mass, not molar mass, is the amount of grams produced from this solution. Now, what it's also asking is the leftover silver ion in solution. Like the concentration of it. So they're asking concentration in regards to moles per liter. So with that being said, we know that the whole solution stayed at 50 mils, right? And to find out the leftover moles, all we're really doing is we're going to subtract this amount that formed the 0.0005 from what we started with, the 0.0589. So if we get that number of what we started with and we subtract 0.0005, our leftover silver, yeah, exactly, it barely changes. It's just 0.0583. Okay. And I mean, it keeps going, so we can round it to 0.584. But that's the amount of moles that we have left, actually. And we know that it's in 50 mils. So actually what we can do, okay, is that we just say moles per liter. Okay, but now we have to make sure that the unit is going to be in specifically liters. So what we have to do is make sure that 50 mils cancel out. There's 1,000 mils in a liter, so these two cancel. So we then divide by 50 for our answer and times it by 1,000. Okay, and we get for the concentration, well, it's actually quite high, 1.1. Well, I mean, to keep it consistent, it would be 1.2 for the molarity of silver ions. Now, you're probably asking yourself, how do you know that it's the ions? Because if we look at it, right, silver nitrate, okay, for every 1 mole of silver nitrate, there's 1 mole of silver ions, because that's the ratio there when you look at it. For example, if you're looking at like the oxygen specifically, it would be 3 moles of oxygen for every 1 mole of silver nitrite. But they would never really ask you that, because nitrate, sorry, I keep saying the wrong one, nitrate is usually together, so it'll still be 1 mole of nitrate ion per mole of silver nitrate. So that's how I was able to just get that number straight from there, because exactly, it's still just a 1-to-1 ratio. So with that being said, we know that the mass produced is 0.072 grams of silver chloride, and we have a whole 1.2 molarity of the silver ions left. Okay, so with that being said, let's see how we did. Exactly, sodium chloride was definitely the limiting reagent, because exactly this number dwarfs it. And exactly the mass of silver chloride form, they did get 0.0715, okay, which is, yeah, we got it rounded. And then the concentration of silver chloride left, exactly, we have quite a high number. Okay, although I would say it shouldn't be mole over mole minus 3. It should just be moles per liter. I still say this is correct. That unit is, it may have just been like a system error, or like they try to put something else. That's what it showed up as, but this is correct. And we do have the same values. I just rounded a little bit differently, just because I wanted to stick with the significant digits of the 2 here and 2 here. We could have gone with a 3 there, but that's it would be this technically more correct to have 2, because you always want to go with the lowest amount of numbers. Okay. Alright, so that was quite a question for number 2. A lot of steps involved, but hopefully you're able to follow along. And now we have something that's quite a bit of a breather, I would say. It's asking us for the molar mass of calcium. Okay, so they just gave it straight from the periodic table, which is fine, but there's the reason why they ask type of questions. They want to actually see if you understand something. Is calcium atomic? Well, let me write a different color. Is calcium an atomic element, a molecular element, or a molecular compound? Why does it matter? Because depending on what it is, we would approach it differently. So an atomic element is kind of just an element that's just by itself. Molecular element is two of those things, or at two or more of the same thing, okay? And a molecular compound is when there's a mixture of different things, okay? So the reason why I mentioned this is because we're definitely not dealing with a molecular compound, because you only say calcium, okay? So we can cross that one out. All right, but on the periodic table there are a list of molecular elements that you kind of have to get familiar with. Typically they're gases. So if you remember, like nitrogen would be like N2, that would be its natural state in the environment. Oxygen exactly would be O2 as well. These are all examples, okay? These are all examples of molecular elements. Now what does calcium do though? Calcium is a metal, and typically metals are completely fine by themselves. They show up in nature exactly like as atomic elements, well, by themselves really. And that is the answer there, where this is what you're looking at. And the reason why that's important, because now that you know that calcium is a type of atomic element, typically as soon as they mention a metal, you can assume it's an atomic element just when it's by itself. That way you can look at the periodic table, and whatever they have as the atomic mass unit is also going to be its molar mass. So exactly with this calcium, if you look at the molar mass, 40.078 atomic mass units, that would actually also be its grams per mole for calcium, because of the fact that it's an atomic element, okay? So just things you have to watch out for, because they can always try to confuse you, like by throwing in certain gases and stuff in your periodic table. They could ask like molar mass of nitrogen. You would not use its atomic mass unit. You would have to double it first, because there's two of them in its natural state, okay? So this is correct. Because they said that it's 40.08, which is from their periodic table would exactly be the right amount as well. And now let's move on to question 4. Okay. This question is asking us, is air a mixture, compound, or element? Okay. Okay. Compound or element. So when you think of air, right, there's definitely a lot more gases in the air, but typically what gases are definitely present, okay? And I'm going to say right now for this one, we don't really need to think about nitrogen. Although there is a certain amount of nitrogen in the air, like nitrogen gas, the ones you have to focus on is what you use to breathe and what plants use as well to do photosynthesis. So typically, the things in air, at least, are oxygen, because we need that to survive, and carbon dioxide, because we breathe that out, and also plants need that to survive. So that's what we know what is in air. Now, when I say air is an element, as described in the previous question, is air, when you see two different things floating, if it was an element, it would look like that, where it's all the same thing floating in I guess air. But you see here we have O2 and CO2. So that would be what the element is. So element in this case does not work. Now if it was a compound, okay, it'd be almost like the same thing, but for compounds it'd be like, this is just an example compound here, everything there would look the same, okay? That is the key for a compound, is that everything there looks the same. And now if we were to actually draw out what O2 and CO2 like theoretically look like, O2 would be more like this, and CO2 would be more like this. Okay, so now would you say that those are the same compounds? No, because those are different compounds. O2 and CO2 aren't the same. If we said air was just filled with carbon dioxide, I mean, for one, we die. But more, then we can say yes, it's just a compound. Now, with mixture, you probably guessed it by now exactly. It's when, now we have to remember that these aren't bonded to each other, but you have a mix. So, hence how that name is there. But you have a mix of different compounds, elements, or whatever really in the air. This is like a theoretical version of what a mixture would look like, where you have some of one thing, some of the other. That's what would constitute a mixture. So with that being said, air in this case is a mixture. Okay, based solely on just remembering that there's oxygen and carbon dioxide in the air. Like I said, there's many more things, so it's even a more complicated mixture. But just by knowing that it at least has more than one different compound in there, it's automatically a mixture. And I mentioned that they're not bonded to each other because this is not just one giant compound of O2 and CO2 attached to each other. They're separate oxygen and carbon dioxide particles, molecules floating around. Hence why it's a mixture. It's like putting like sand and salt and sorting that. Okay, you no longer have just a lot of sand or a lot of salt. You have sand and salt in there. So it's a mix. Okay. So the air we breathe has like nitrogen and O2, and inert gases, water vapor, and other gases, carbon dioxide. So there's a lot of stuff in the air, as it even says there. And just by knowing is like there's at least one different thing, we know that air is a mixture. Because if I were to try to break down every single thing that is in the air, we might be here for a while. So just understanding that there's at least one does help quite a bit. And now let's move on to question 5. What is a molar mass of sodium carbonate? Okay, and they're nice just to give us actually the molecular formula for it, Na2CO3. So with that being said, just as a crash course in naming, we had the 8. Just remember, these are things you have to memorize, but it's going to be the, I guess, carbon part, okay, plus a certain amount of oxygens, okay. So that certain amount of oxygen is the part you have to memorize. So there's a list of all these ions really, and those ions, based on, I guess, exactly their amount of oxygens and everything else, have certain names with them. So carbonate, there's also carbonite, but we're not going to get into that. Point being that we have ATE, that's the highest typically amount of oxygen you can have. So with that being said, it has a charge based on what you can see here of by itself is CO3 2 minus, okay. And sodium, exactly, you can just take it straight from the periodic table, and you know it's in the first row of the periodic table, so it's just Na plus. So as in that's the one to get rid of. And you know, as if you see my previous videos, I really like to emphasize the electron configuration. So exactly for sodium, we start with helium, I believe. I mean not helium. We start with neon. That's the second row, and then it just be 3s1. Hence why I want to get rid of that 1. Okay, so that was just a quick little lesson there. But point being though is that for it to balance in terms of to have a net charge of 0, you need to double the sodium, and hence we have Na2 and then the carbonate. So with that being said, to find the molar mass, we just list down the constituents: 2 sodium, 1 carbon, 3 oxygen, and then we just work through it carbon is 12.011, and oxygen is 15.999. That's, oops, I don't want to do that math. 22.990 times 2, 45.98, 12.011, and 47, whoops, see? 45.997. Okay, and the total we get when we add all these three together is 103.988. And that is what we get for the molar mass of sodium carbonate. Let's see how we did. Exactly, so 3 times 16, 48, 12.01, 45.98, adding together 105 point, oh, that's strange. It should be a little bit closer than that. Because they have 22.9, that's 45.98, 12.01 for carbon. Wait. 15 times 3 is 45. Oh, I didn't factor this part. It's going to be 47. This is why you always want to check your math, because it's going to be 47.97, not 45. So, always use a calculator if you're unsure, just to do math that you may not find simple. Even if it does look like simple math, use your calculator still, because you don't want to lose marks in a very foolish way. So exactly, now I have 105.988, which makes more sense, because even if you're using different periodic tables, the difference should really be like in the decimals, like point something. You should not have a difference of like 3 grams. That's something was added wrong. And this is correct. So with that, let's move on to question 6. And now let's see, what is a molar mass of lead? Okay, so for this question, exactly just as how we did from the previous one. Okay, is lead a molecular element, a molecular compound, or an atomic element? So lead is just straight from the periodic table right here. Where's PB? There we go, lead. Okay, and it's considered a post-transition metal. So it's considered, we can find it on the table. We know that that is not like a shorthanded version of some compound or anything. So we know it's not a molecular compound. When it comes to being a molecular element, we know that lead is not a gas, and when it comes to, like, its natural state, it's just by itself. So it's not a molecular element either. It really is just an atomic element. So because lead is an atomic element, there's nothing else you need to do to it. You take it straight from the periodic table, its atomic mass units. So 207.2, and that is your molar mass of lead. 207.2 grams per mole, because lead is an atomic element. Okay, just something you always have to look out for, because exactly, you don't want to get too comfortable, because they ask something like, what is the molar mass of chlorine, for example? That one shows up as Cl2. You don't want to just get to the atomic mass unit really quickly, because you have to recognize that chlorine is a molecular element, meaning that you'd have to double, because of 2, you have to double whatever is on the periodic table to get the actual molar mass of chlorine gas. Ooh, that was nice. But yeah, so 207.2. Exactly, because they just took it straight from the periodic table. And yeah, and the key thing is because lead is an atomic element. Okay, so this is also correct. So now let's move on to question 7. The formulas for magnesium oxide and carbon monoxide look very similar. What is the name of each compound, and why do we name them differently? So I'll definitely just give away the answer right there, but let's just write down what it says. Formula for MgO and CO look similar, and name of each compound and why name differently. Okay, so for this, actually, we're actually going to approach the second question first, why we name them differently. Let's look at what let's look at what MgO is consisted of. Okay, we have magnesium, so MgO, we have magnesium and oxygen. Okay, CO we have carbon and oxygen. Okay, so just want to change that over. So start with MgO, right? Magnesium, if you look at the periodic table, is a type of metal. Okay, oxygen is a type of non-metal. Okay, so if you remember, what does that make magnesium? What does that make MgO? It makes it an ionic compound. That is a key thing. This is an ionic compound. Okay, and carbon is a non-metal. Okay, and oxygen, as we discussed, is also non-metal. So now we have two non-metals attached to each other. This is a covalent compound. Okay, so the thing is that, why did we name them differently? Because we have different naming rules for ionic and covalent compounds. Okay, and that is literally the basis of it. It's just different naming rules for ionic and covalent compounds. Now let's delve into what we would actually name it. So magnesium, MgO, magnesium and oxygen, the way you would name that, right, is that the goal here really is to put magnesium and oxygen. Okay, and what we do is we drop out the suffix for most of the oxygen, so we only left with the OX. All right, and then we add IDE. The key thing, actually, before I even get into that, we're going to now approach carbon and oxygen. Quite similar naming structure. Okay, we have carbon, oxygen, then we drop that suffix and add the IDE suffix. But here's where the extra step comes in for for covalent compounds. Okay, you need to have the prefix indicating how many of your second elements you have. There's only one oxygen, right? So with that, we have to use the prefix of mono. So that is actually a key difference there between naming ionic compounds and covalent compounds. Ionic compounds, you do not put the prefix indicating how many you have of the second element. For covalent compounds, you have to put the prefix indicating the amount of the second element you have. So this would be the name for CO, carbon monoxide, and this would be the name for MgO, magnesium oxide. Okay, and exactly why name differently? Oops, that's a little too far. Carbon mon right here, and magnesium, nothing there. Why different? Because one is an ionic compound and one is a covalent compound. Okay, so ionic compound, no prefix. Covalent compound, always a prefix. Okay, Okay, so exactly, they're identifying. That's a lot of steps. They are being a lot more specific in regards to like identifying the metal and identifying the non-metal, and just making sure that you are identifying the right parts, because like we had in the previous question, it doesn't have to be the metal non-metal parts don't have to be all one thing. For example, if you think about, typically if you have a metal and we had Mg magnesium carbonate, for example, this whole part would be the non-metal part, instead of it just being like the carbon and then the oxygen. It'd be that whole part is a non-metal. And then they identify the anion, and then you put the names together, and then you just drop the end and add the right suffix like we did for oxide. And then this is going to the details of how to name covalent compounds, which is what we have for carbon monoxide, since it's just two nonmetals together. So with that being said, they say magnesium oxide is ionic, carbon monoxide is covalent. So we name them magnesium oxide and carbon monoxide respectively. So yeah, this is correct. And exactly, I did scroll down slowly, so if you need to pause the video to kind of go through the steps of what they were saying there, you definitely can, because that does break down in terms of how you actually, like, you know, distinguish which one is a cation and the anion and such. I just wanted to focus for this question specifically on just, you know, finding out what the name difference is of the compound. Now, for this question here, okay, density of silver is 10.5 grams per centimeter cubed. Okay, that is the density. Okay, they're asking now for volume in centimeters cubed of 0.443 kilograms. And if the sample of silver is a cube, how, if cube, length of each side, okay? And C, how long is the edge of this cube in inches? Okay, so now with that being said, you may think this is more of, I guess, physics math conversion question, but chemistry and physics are quite intertwined once you, especially when you start getting into the smaller particles and their forces and everything. You start seeing a lot of similarities there. But aside from that, let's delve into this question here. Okay, we know the density is 10.5 grams per centimeter cubed. Now, if you did not know what the formula for density is, there is a way to bypass that. As it gave us the volume is, the mass, right? And you see the units that we have here, you can actually set it up to where you don't need to know the formula for density, but you can still solve for it. And it's called by making sure that you actually cancel out your units. So we have 443 kilograms, but density deals in grams, right? So first let's get this over to grams. So for every kilogram, there's 1,000 grams. Okay, now we have the grams in the numerator. The density of silver is 10.5 grams per centimeter cubed. So if we flip that over to cancel out grams, it'd be 10.5 down here. So in a sense, what we've done is that we've still solved for the volume without knowing actually the relationship between volume and density. Okay, so we have 0.443 times 1,000 divided by 10.5. Okay, and we get 42.5 I would just round 2. Okay, centimeters cubed. Okay, so the actual relationship, though, because it is something important to know, it's actually going to be, so as you see here, right, to get the volume, right, we had to divide the mass by density. So to get the volume, we have to divide mass by density. So to rearrange this to know the density relationship, right, we would actually have density, okay, because now we move it over, density times volume, and then we have to divide now volume from both sides, is mass over volume. This is the relationship if you just want to use a formula. But this way just shows that it's quite important to keep track of your units, because sometimes knowing all the formulas can be overwhelming. But if you know what you're looking for in the units you have, you can still solve for things without knowing exactly the relationship. Okay? So, with that being said, if it's a cube, what's the length of each side? So, if you know how to solve like the volume, I guess, of a shape, okay, it's length times width times height. But when it's a cube, that means length equals width, which equals height. So that would mean actually we just have 3 of the same things cubed, okay? Hence how we have centimeters cubed. So to find just x, right, since we know that centimeter cubed right now, the total volume is 42.2 centimeters cubed, we have to now do the square root to the 3rd power of the 42.2, and that's how we get what just x is. That would be the length of at least one side in centimeters, just because you have to keep track of units. So the 42.2, now let's do this square root of it to the 3rd power, okay, and we get 3.48, if you round it there, centimeters. That is the length of one of the edges, okay? Alright, so now they're asking for that length in inches. Okay, so if we go to our little conversion sheet here, length, 1 inch is equal to 2.54 centimeters. So what we do here, okay, is that we have 3.48 centimeters, right? And we're trying to get to 1 inch now. So 1 inch is going to be at the top, and we have 2.54 centimeters at the bottom. Cancel out those units. So divided by 2.54, the length of inches is equal to 1.37 inches. That is going to be the length of this cube, like the one side in inches. Okay, so with that, let's see how we did. So exactly, they got the volume, which is perfect, 42.19, and then they did this square root to the 3rd power, and they got 3.48, and then they converted over to inches, which is the 1.37. So with that, this is correct. And let's move on now to the next question. Question 9. What is the molar mass of aluminum sulfate to the nearest gram? Okay. So molar mass of aluminum sulfate. So with this, we kind of have to break it down like that previous question of what this is made of. We have aluminum and we have sulfate. We're gonna solve the sulfate part, not because it's easier, but more so because it's just solely based on, unfortunately, memorization. So we have sulfate, which means it's a sulfur and a certain amount of oxygens with a charge because it's an ion. So with sulfate, that is the one that has 4 oxygens with it, and it's going to be 2 minus. You can actually even check it using the electron number, because you'll notice that oxygen typically likes to be -2. So there's 4 of them. This is -8, right? Okay, and sulfur, because it's the 6th, well, not 6, it's the 16th column, it's usually 6. In this case, because you want to balance it out, it'll be +6 in this case. So as you can see here, these two numbers do indeed equal the 2 minus that we get from sulfate ion. So that one is something you have to memorize and get comfortable with, because every ion has a typical charge, and it's highly dependent on how it ends. The ATE, or it can be sulfite, which would be SO3, for example. But just there's a big sheet. It just goes down to practice. The more you use these ions, the more familiar you get with them. Now, aluminum. It's right here on the 13th column. Okay. So as we've been doing, we've always been drawing out the electron configuration. It's neon, and then it's going to be 3s2 because the first 2 columns are filled, and then 3p1. So that means aluminum would have an easier time getting rid of 3 than adding 5 whole electrons to become, like, you know, a noble gas structure. And you can also just say, because it's in the 13th column, that's the same thing as well. It's like doing the electron configuration, because it doesn't hurt to practice. So we have Al3 plus and SO4 2 minus. So for it to have a net charge of 0, we need the lowest multiple between 3 and 2. And that would be 6. So that means we have to multiply this by 3 and this by 2. So now, in total, for the actual aluminum sulfate structure, we have Al2 SO4 3. That is the molecular structure of aluminum sulfate, the molecular name. So with that being said, now we have to find out the molar mass. So it's back to getting the constituents. So it's 2 aluminum, and then we want to apply the 3 to every part in there. So that's going to be 3 sulfur, and now it's 4 times 3, which is 12 oxygen. So that's going to be quite a big molecule. So 2 aluminum, so that's 26.982. Sulfur is 32.06. Oxygen is 15.999. Oops. Okay. And now, so 26.982 times 2. Okay, 53.964. Okay. 32.0. Where is it? 6 times 3, 96.18, and 15.999 times 12, 191.988. So we add all those 3 together. Alright, and we get 342.132 grams per mole. So yes, that is quite a big compound, and exactly, it makes sense because it's so aluminum is twice and the whole sulfate ion is 3 times. So yes, it makes sense that it's going to be that big. So with that being said, let's see how we did. So exactly, they say that's given by the chemical formula Al2 SO4 3. Oh, I almost forgot the last step. To the nearest gram, because we could have gotten this question wrong easily. Nearest gram would mean that we round, and because it's 1, it's going to be 342 grams per mole. That is why it's very important to read and write down the whole question to nearest gram. Okay? because you don't want to lose marks just by overlooking small things here and there, because you literally did the brunt work by even getting the molar mass to begin with. So just check what the question is asking for, okay? So with that being said, let's see how we did. Oh wow, that's embarrassing. Not like embarrassing like haha, but more so like, yeah, exactly, they almost did what I did. So 26.98, 342. I'm just looking at numbers. I'm not sure how they got that number even. I mean, they are close, but when I add 53.96 plus 96.18 plus 192, it's 342.14. Okay, so it should be 342.14. I only saw it as weird because the only number that was different was my oxygen, and it was actually a lesser value. So I don't see how they could have gotten a lesser value than I. That's why I'm just doing a double checking. But overall, sadly, this is incorrect because they ask to the nearest gram. So it's 342. But exactly, I can't really say much because, as you saw, I was about to do the same mistake as well until I remembered when I went back to the question. So let's move on to question 10. Lesson here is, it doesn't matter what level you're at, always check back on what the question is asking for. Best way to make sure you get good marks. So now we have this question here. Is HCl a strong acid or base? So to find out this question, actually, personally for me, there's literally two options here. One, either you have to memorize this, or if you're gone into the higher levels of chemistry, you need to find out, okay, its Ka value, which is the dissociation constant for acids, okay? Simply put, if your Ka value is greater than 1, okay, this is a strong acid, okay? And if Ka is less than 1, but it's still greater than 0, this is a weak acid, okay? So this question is asking if it's a strong acid or a base. We'll get into that, but first we want to see how HCl actually reacts with water. So as you see here, we have chlorine, okay, relaxing by itself, and then the hydrogen attached to it, okay? And this is actually stable. Chlorine really likes this, but it also doesn't mind because it's actually quite selfish. It doesn't mind if this hydrogen were to skedaddle, get out of there, forming the chlorine ion, as we are also familiar with, okay? So because it actually has a proton to give away, this is known as Bronsted-Lowry acid. So now we at least get a hint of what this answer would be, okay? Because exactly, it's giving away its proton, so it does count as an acid. In fact, if you write down the whole formula for it, it'd be HCl plus water, because that's usually what it's into the solution. And it would actually completely, well, actually we don't know that yet. It would, we're just gonna put the line like that, okay? It would go over to form, whoops, Cl minus plus H3O, okay? Making that this HCl is going to be the acid, this is a conjugate base, and H2O is going to be the base, and that's its conjugate acid. So it also follows as well that because it goes from acid to conjugate base, it's giving away an acid, so it's giving away a proton, which supports it more that it is indeed an acid. Now to find out if it's strong or weak, we just go straight actually to this sheet here, or you've memorized this. As we stated, Ka has to be greater than 1 for it to be a strong acid. So we look at where hydrochloric acid is. Okay, it's all the way up here. So with that being said, any value anything that's above hydronium ions, as you can see here, hydronium ions at 1 for the Ka. So anything above it means that it has a Ka greater than 1. And it even says here that strong acids completely dissociate and they have a Ka greater than 1. So with that being said, if HCl is a strong acid or strong base, okay, we know it's working as an acid. So now that we know that its Ka value is greater than 1, this is a strong acid. So hydrochloric acid is a strong acid. And also, I know we refer to the Ka value and some of the dissociation constant, but these are some things as well that you most likely have to memorize, especially if you haven't touched anything about dissociation constants. Is that there's certain strong acids right there. I mean, there's certain strong acids that exist in nature, and this list is just a few of the ones that you do have to, well, I mean, not a few actually. These are the lists will probably have everything you probably need to memorize of which ones are strong acids. So hydrobromic acid, hydrochloric acid, sulfuric acid is a common strong acid that people talk about, and nitric acid as well is another strong acid that people talk about. Okay. So we have the right equation here, and with that being said, it's a strong acid. They say that because HCl easily gives up a hydrogen ion, but that's usually explained by its Ka value. Other than that, you pretty much have to memorize that, because you wouldn't know from the equation that it actually goes like that, as in there's no back and forth where you have like this. It just goes straight to forming the chloride ions and H3O. So this is correct though, because they did identify that this is indeed a strong acid. That's one of the question 11 here, with a quick water break intermission. Always important to stay hydrated. Now we get a little bit of a easier question because they give us the information, but it's asking us to find molar mass of CaNO3 2. So I know the question is not asking this, but if you wanted to name it, you just break it apart to its constituents. We just have calcium and a nitrogen with many oxygens. So this would actually be nitrate. That would be the NO3. Okay, so the name for this is calcium nitrate. Okay, so with that being said, to find the molar mass, constituents time, 1 calcium, you apply that to both the nitrogen and the oxygen, so you have 2 nitrogen and 6 oxygen. Okay, and calcium was like 40.078 or something like that. 40 point, yep, because we just did it earlier today. Nitrogen is 14.007, oxygen 15.999. Okay, so 40.078. Nitrogen times 2 is 28.00014, and we're not making any mistakes with the oxygen this time, so we're going to just do it in the calculator. 95.994. okay, and then we add them all together. 28.014 plus 40.078. We get 164.086 grams per mole. Okay, so that would be the molar mass of calcium nitrate. Okay, so exactly 1, 2, and 6, perfect. Add them together, 164.098. Exactly, and ours is different because the nitrogen was rounded here and the oxygen was rounded as well. So that's why they have a slightly larger number than ours. But exactly, as you can tell, the difference is still just in the decimals. So we still have that 164. So this is correct. And in fact, before I move on, I'm going to make sure that they don't ask anything like to the nearest gram. Okay, good. It's just find the molar mass. So exactly. We both did it correctly. We weren't missing any information. Now move on to question 12. What is the electron configuration of selenium beyond its noble gas? We've had a lot of electron configuration practice. For those that are just joining in, if you ever have the time, check out the previous videos and such, just because that's like our favorite question. I'm always trying to bring up electron configuration, mostly because actually like that's one of the things that I struggle with, because it can get really complicated when it gets into the farther shells. But with that being said, we have selenium. Okay, it asks beyond its noble gas. Okay, so electron configuration of selenium beyond noble gas. Okay, so with that being said, actually I'm glad they said beyond noble gas, because we can use a shorthand version for the electron configuration. So we start at the noble gas that comes up right before selenium. Selenium is element number 34 right here, so the noble gas they're referring to is argon. Okay, and now we go through filling out its shells, its subshells. We have 4, because it's on the 4th row, 4s2, because that implies the first 2, right? Then we have this whole row right here, the transition metal row. That'll be 3d, because we want to subtract 1, because it's actually in the shell prior. 3d, and all the way to zinc, that's 10. Okay, and now selenium, we now enter the p subshell, which goes back to the same subshell. That's 4 again, p, and then you have 1, 2, 3, 4. So this will be the electron configuration of selenium beyond its noble gas. We have to rearrange it real quick, because you would actually have it, okay, still argon, 3d10, 4s2, 4p4. Okay, so this is what we have here. Okay, now the reason why we organize it, because as you can see here, just extra information, you can kind of tell that in terms of valence electrons, selenium would only have 6, not 16, but just 6, because that d shell counts as a prior shell. Hence how you actually see it here, it matches perfectly. It's on the 16th column. Okay, meaning that selenium would most likely want to just get 2 more electrons to be a noble gas. Okay, but that would be it for that question. Let's see what options they have. So beyond noble gas, so this actually is a noble gas, that's D. Okay, so let's actually list down really the options. Okay, so A, 4p4, B, 4s2, 4p4, C, 3d10, 4s2, 4p4, D is just silver. So its noble gas actually, as we even used, is literally the argon, so that one's not even going to be an option. And now the electric configuration beyond it, we literally now have been able to solve the whole thing, so we just kind of match. We know it's not just 4p4, we know it's not 4s2, 4p4. The only answer here is C. Okay, but yes, right away you could have crossed out D, because D is the abbreviation of the noble gas itself, so that would never be the answer, unless they ask what is the noble gas abbreviation for selenium, which would be kind of a very weird question. That's the only time where you pick D as an answer. So exactly, answer is indeed C. Okay. Now, I realized that when I was explaining it, I kind of said, yes, this is the D shell, this is the S shell, this is the P shell. The way you work through that, there's definitely going to be more questions that come about, but the main thing is that if you look at the periodic table, The S subshells are column 1, column 2. When you hit and you start counting through the transition metals, that is your D subshell. So column 3 to column 12. Once you get out of that, 13 through 18, that is your P subshell, okay? And the only exception is helium. Helium actually counts as an S subshell. So you can kind of ignore helium. Helium would be kind of like next to hydrogen right there, if it could. But it is a noble gas. And then the last subshell, the F, is when you hit your lanthanum and actinium series. That is the F subshell down here. So that's why they just kind of go like this is D, this is S. And then the important things to know is that for a D subshell, whatever row you're on, it's -1. Hence why we have 3. And for the F subshell, whatever row you're on, it's -2. Okay. Just wanted to go over that because it can seem like I'm just like, okay, this is that, this is that. I just want to explain the basis of it. There's a lot more detail that comes to it when it comes to electron configuration. And look at that, we're getting real lucky. What is the electron configuration of silver? Okay, so with this, I still genuinely prefer to just do the shorthand version as much as I can, because it just gets really tedious, especially when you know the electron configuration. But for y'all, I'm gonna go through and go from the beginning. I'm still gonna do the shorthand version after, but this is how we start. It's like we're counting through the periodic table. So in the first row, we have hydrogen and helium. So it'll be 1s2, okay? Because first row and then S are for hydrogen and helium. That was the only exception. Now move on to the next row. 2s2 counts for lithium and beryllium, and 2p6 all the way to neon. Okay, those 6 over there. And then we do the same thing. 3s2, that was I believe it's sodium and magnesium. Yep. 3p6. 2s2 was lithium and beryllium. I don't know what I said there. I just want to clarify that. And 3p6 is all the way from aluminum to argon. Okay. And then we have 4s2, which is potassium and calcium. And we count through this whole D shell. That's 3d10. Remember, we subtract 1. Okay, that's why we have 3d10. We can reorganize it later. We're just going through them. Okay, and then 4, back to the 4p6. Okay, and we're trying to get all the way to silver, and we're close. Okay, because 4p6 now we've done it all the way to krypton. Okay, so if we wanted to shorthand that whole thing here could be written just as this. You can see why I like the shorthand. But yeah, now we have the 5. So 5s2. In fact, let me draw this in a different color because this is not the new stuff. Okay, and then we want to get to silver, so we count 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it will be 4d9. Okay, so now this is where it's actually better to draw the orbital notation as well. I'm only going to do the orbital notation of the outermost shells. So we're going to have krypton abbreviation and the orbital notation. 2, 3, 4, 5, 6. So remember that because the D orbital has a lower number, okay, it comes first. So 4d, 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 4d. So this is a 4, not a 9. Okay, and this is now the 5s. So right now what we have is 5s2, as it says, like that, 2 electrons spinning opposite of each other, and then 4d9. So we start like that: 1, 2, 3, 4, 5, 6, 7, 8, 9. So this right here, the reason why I drew it like that, because this is one of the elements that follows an exception to where it's like, as you can see here, it could keep its 5s filled, or it could actually fill its D subshell, which it would actually prefer, because the fact that there is quite energy level difference. And exactly, just really trying to, if it costs not much energy to transfer literally one electron, you notice most of the exceptions are around the 6th column and 11th column, because in the 6th column we have typically 4d4. I mean, not 4d4, we have d4, and if it has its s filled, which it has to, because to get to d you need to fill your s shell, right? It would give up one of its s electrons to make it like from d4 to d5. Same thing here, where you typically see like the 11th column. There are exceptions that you just have to simply memorize, but this is how I kind of visualize them. In the 11th column, it's like close again. 4 was d9, and it's really close to just having 10, right? So it's kind of like, you know what, I would take it from my S shell and make myself just have the 10. It's almost like a mini version of the octet rule, if that makes sense. The reason why the D4 works is because in D4 there's one electron in each shell, and it's like I might as well just get that at least half done, hence why it would be the 5th one in the 5th D subshell. So with that all being said, this is actually what we'd have. So now that we see it visually, it would actually be 5s1 4d10. So if I wanted to rewrite this, I'm going to do the shorthand version, just a disclaimer. It's going to be krypton, okay, 4d10 5s1. This is what I would have for silver. And it actually makes sense too, because silver typically moves around as an ion. It's just silver plus, like that. This is why, because it actually prefers, in terms of its energy, to actually just have the other one in its previous shell, meaning that it really only typically has one valence electron in its most outer shell instead of 2. So yeah, just a little fun fact there. Now let's go back to the actual question. Well, this can happen because exactly, the exception is something that you have to really. That's why I like to draw it out in the on the electron configure, the orbital notation, because it makes a picture, to me at least, just a bit clearer of what silver would prefer to do. And it is actually one of the exceptions, so this is incorrect, which is probably why they ask this question, because they want you to get familiar with the exceptions. Krypton 4d10 5s1. And to make sure I'm not just saying this without any basis, check this out. Electron configure silver 4d10 5s1. So I'm not crazy. These are just one of the exceptions you have to know. Okay, so let's move on to question 15. Okay, so what is the molar mass and name of the compound NiX3 if it's 19.67 nickel by mass? Okay, that's kind of tricky actually. So molar mass of compound NiX3 if it's 19.67% nickel. Oh wow, that's a bad nickel. Can't even read that. Nickel by mass. Okay, that is very crucial. Okay, because what that is saying, okay, is that 19.67 grams of the whole 100 grams of that compound is purely nickel. Okay, so with that being known, right, this is where it gets a little bit tricky, right? We refer back to periodic table because we need to know the where is it? Where's nickel? There we go, 58.693. We actually need to know the molar mass of nickel to, in a sense, try to convert, because exactly for every 100 grams, there's 19.67 grams of nickel, okay? So then to be able to find the molar mass of the whole compound, what we first have to do is understand that, how do I put this? We actually start with the nickel, right? So we would actually convert that to moles. So this is the theoretical number, okay? So we have 19.67 grams, right? And just move all this, okay? And then we wanted to convert it to moles. So remember, for nickel, because we just see a face value, okay, it's just going to be 50, oops, wrong place. 1 mole of nickel is 58.693 grams. We cancel these two out, okay, and then we get that it's going to be 19.67 divided by 58.693, okay, and we get that it's 0.335 moles of nickel. But they're generous enough to tell us that it's NiX3, okay, meaning that for every mole of nickel, okay, to form this compound, there has to be 3 moles of whatever is there. So with that being said, actually, 3 moles of nickel, right, Ni, okay, so that's 0.335 moles of Ni, okay, and so as we said, for every 1 mole of nickel, there's 3 moles of X. So we multiply that by 3, we get 1.01, keep it same significant digits and stuff, moles of X, okay? But now that we have this, right, what does that mean for the I'm just really blanking out, sorry about that. What does that mean for that? If 19.67% of the nickel is, if 19.67 of the 100 is nickel, that means if you subtracted to find what the mass of X is, right, if you subtracted 19.67 minus the 100, right, that's the amount of mass you'd have the other part. So 100 minus 19.67, okay, that's 80.33 grams, okay? So with that being said, that is going to be the theoretical grams there, and that means that for the X, right, we're going to divide that per its moles to be able to get now its theoretical molar mass, okay? So that means 80.33 grams divided by, that's where you did the math, 1.01 moles is equal to 79.9 grams per mole of the X, okay? So now we have, as we solved here, the molar mass of nickel and the molar mass of the X. So now we have, we did the now math of the constituents. We have 1 nickel, okay, 3X times, okay, and that is 58.693, 79.9, okay, 58.693, 79.9, oops, sorry, times 3, that's 239.6.7, add them together, plus 58.693. The total we have is 298.38, but let's make sure we round it correctly. 19.67, so we want 4 significant digits as our total answer, so 298.4. So grams per mole. This right here will be the molar mass of a compound. 19.67 of it was made up by nickel. Now the cool thing is you can actually check your answer. So what I'll do is that we have our grams per mole. So let's say we had 298.4 grams. If we divided that by the 58.693, because what we've really done is that we've pretty much said that that number for nickel should constitute of 19.67% of it. So let's see. So that's 58.693 divided by the answer we just got, 19.67. So exactly, we did do it correctly, because this grams per mole here for our total molar mass actually says that yes, when you look at the mass, nickel does constitute of almost 20%, like the question said. So let's see here if we did this. Yep, we had that. Oh, they did it a lot easier. I tried to break it down to the steps, but I did get the same. And exactly, they did say, okay, they go into more detail here, which is what each x must be. So I'm glad I got that part. So they have molar mass. I want to see what the thing is asking for. Molar mass and name of the compound. Oh. You see? Always read the whole question. So the name then is what? Okay, so let's look at the periodic table. What element has close to 79.9? Oh, there it is. Bromine. So nickel's here, bromine's here, so NiX3 would be, that was a little embarrassing. I gotta start reading the whole question. Although this part was probably the easiest part considering we've done everything else. Okay. It would be NiBr3. Okay. It's still very important that you keep reading the whole question so you don't lose silly marks. Because technically, if I had submitted this work, I would have missed like a whole second half of the question, which was honestly probably the easier part after I've done all the math. So yeah, molar mass, correct, and name. Okay, and now let's scroll down as we got here. Exactly, it is nickel bromine 3. Well, I mean, it's just nickel bromine, because nickel's a metal. Nickel bromide is what you'd say, yeah, because we want the same ending, the IDE, and it's a metal and a non-metal. So nickel bromide. Okay, let's move on to question 16. Yes, it is 16. Sketch the resonance structures of the nitrite ion. Describe the electron pair and molecular geometries of the ion. From these geometry, decide on the OMO. I think they meant ONO bond angle. The average NO bond order and the N atom hybridization. Okay, so that's a lot of information here. So let's start with the nitrite ion. Okay, so it's NO2 minus. Okay, so let's just we have to really think about this one. So Let's start with the easiest part of just drawing the Lewis dot diagram. So nitrogen, okay. In fact, I'm just gonna write down the whole question so we don't miss anything. So resonance of NO2 minus, describe electron pair and molecular geometry of ion, and decide O and O bond angle, average NO bond order, and an atom hybridization. This is a wow layered question. Let's start with what we can do. NO2, okay, minus. So we know nitrogen, okay. We can say that because it's on the 15th column, and also because when you draw the electron configuration, it's He2 S2 2p3. Okay, and oxygen, exactly, it's on the 16th column, and it's also He2S2 2p4. So you can see here that 15th column, 16th column, nitrogen has 5 electrons to work with, oxygen has 6, so times 2, and then this is just an extra electron, so that's plus 1. So 5 plus 1 is 6, plus 12, 18 electrons total. Okay, and now let's actually try to draw this out. So we have nitrogen most likely in the middle, okay, 2 oxygens on each side, and now how many electrons does each one have left? Oxygen has, if we did that, it's sharing 1 right now, so 2, 3, 4, 5, 6. Same thing, 2, 3, 4, 5, 6. And nitrogen is sharing 2 so far, so it'll be 3, 4, 5. Okay. So, and there's also an extra electron, but first, before we include that extra electron, let's see how we can get rid of some of these single electrons. So this nitrogen actually, and this oxygen here, use a different color to really show it, they would actually form another bond, because that would be the easiest way to satiate their need for the octet rule. Now, because these two form another bond here, this oxygen is kind of like, hey, what the heck? Which is where now that extra electron came in. So if we redrew that, okay, it would be N O O okay, it'd be like this. And to find out where the negative charge is, okay, we do some of the electronic number calculations, where we say, so nitrogen has 5 valence electrons minus, it has only 2 in its lone pair, and it's sharing 6 electrons, and that does equal 5. Oxygen on the right, it's 6 minus is 4, and it's also sharing 4. That's also 0. But the oxygen on the left, okay, it's 6, and we have here, it actually has 6 6 electrons by itself, and it's only sharing 2. So this is where the -1 is. So that's where that negative charge is, okay? And now, the first thing they're asking for, though, is the resonance of NO2. This double bond right here could have been applied to either side, okay? So if I was to actually draw it, okay, it would look like this. Okay. we have the O, and this double bond is bouncing between the two, indicated by the dashed line. Okay, and I think, yeah, I can do it a little better. Okay, that is actually what we're working with here, because it could bounce between the two. We just know that they have at least this, okay? Because this double bond could switch over to this side, and that means, well, actually, this could move over here. Like this double bond, the oxygen could claim this whole thing, making this oxygen now form a double bond with the nitrogen right there. So that's what could happen there. Hence why we have it bouncing like that. But we know that it at least has 4 electrons it has to itself, aka doesn't have to share. And same thing with this oxygen here. Just gotta make sure. Oh shoot, there we go. Okay, so that at least answers the question of what the resonance structure is. Okay, so if you want to describe the electron pair and molecular geometry, remember that the electron pair is just simply the things it's attached to. Okay, looking at those structures just a bit easier, because you see here it has 1, 2, 3. The double bond does not count as multiple things, it still counts as one thing it's attached to. Okay, so the electron pair geometry, okay, because it's 3, it's actually going to be a trigonal planar, because typically the ones look like that. This is going to be the electron geometry, EG, to make it easier. Now, the molecular geometry is when you get more specific. It has 2 bonds, so remember, you don't differentiate between single and double. It has 2 bonds and 1 lone pair. So because it has 2 bonds, so molecular geometry, 2 bonds, 1 lone pair, okay, it's actually going to be bent. Okay, because as we said, the lone pair likes to just push everything. So instead of it being like nice and even 120 degrees in each section, the electron is a jerk. I mean, the lone pair is a jerk and squeezes these 2 sides. So the angle for this, okay, I think it's completely justifiable just to say that it's less than 120. So this O and O bond angle is less than 120 degrees. Because we sometimes don't really know the exact amount, but you just know that the electron lone pair is pushing these together. So this exactly is less than 120. It's no longer perfect like each 3 slices of a pie. Okay? So with that being said, we've now done electron pair, molecular geometry, bond angle, average bond order, and hybridization. So the hybridization based on the electron the electron geometry is actually still going to be, because it's 3, right, it's sp2 hybridized for the N atom, and that's what they're asking for here, not the oxygen atom, just the N. Although oxygen as well would also be sp2. Everything here will be sp2 specifically, because oxygen, even you see 2 lone pairs and 1 bond. Actually, that one's a little bit trickier because it's the resonance structure. One side, this would be more sp3, and this would be sp2. But yes, for nitrogen specifically, is sp2. Now, the bond order average. I want to, not too familiar with this. I'm gonna guess and say it's 1.5. Because that is really like, yes, it has in a sense 1.5 bonds in each part, because they keep sharing. It's not 1 bond here and 2 bonds there. It's kind of like 1.5 in each part. But I probably got this one wrong, but let's see how we did for the rest of it. So that is the resonance structure. I definitely drew it like this because this is another way to show it when you have this dashed line. Exactly. So that's part we've gotten. Trigonal planar, electron pair geometry, awesome. And now it's telling us it's bent. And you can actually even verify that here. We have 3 electron groups and 1 lone pair. It is indeed bent. Okay, and this is the approximate 120, but exactly because of the lone pair, it's going to be just less than 120. So having bent molecular geometry indicates that the bond angle between atoms is 120. Not necessarily, like I said, the electrons will push the bonds closer to each other. The central atom has an atomic hybridization of sp2, nice. And now the bond order of nitrogen of this ion, the nitrite ion, is 1.5. Nice. So it did work because like there's 3 bonds in total that's sharing. So it's like you kind of just divide by 2. 3 divided by 2, so it is 1.5. Cool. I'm really glad I got that bond order because that one threw me for a loop a little bit. Okay, but this is correct. We got every part. We drew the little diagram. I'm gonna box that actually because this would be what the hybridization looks like. Something else you can draw, ignoring the angle obviously, but exactly. You'll notice that, you know, another example of like benzene, you know, when you draw benzene out, they don't make you draw every single type of you know, different structure, because I mean it's not that many, but still it's annoying. You just draw like that to indicate that there's a resonance in there. Okay, but if they're asking specifically for each of its resonance structure, then I would go ahead and put each one you see. So it would be the NOO and the same thing, but with just that. Those will be the 2 different resonance. Whoops, sorry, got a little bit too crazy with the dots. So yeah, these will be the 2 resonance structures. So let's move on to question 17, I believe. I think these are some very intense questions we got here. Oh, and then we have this: how to find pKa from Ka. So this one, relatively straightforward, but the thing you have to remember is that we treat pKa and Ka. So how to find pKa from Ka. We treat pKa and Ka like pH and the concentration of H3O plus. So if you remember, right, pH is equal to negative log of H3O plus. So if we follow that logic to where that relationship still exists with pK and Ka, pH, whoops, pKa is equal to negative log of Ka. So what this means actually is that based on the dissociation constant, there is I guess appropriate I guess acidity value, like pH value, that, you know, the acid would like to be at. So what that's pretty much saying is that if you had a Ka value of, I don't know, let's use acetic acid for example. Okay, acetic acid is all the way down here. Its Ka value, right, is 1.76 times 10 to the negative 5. Okay, and this usually is when it comes to buffers, for example. But if we did the pKa, right, it would be negative log of that, 1.76 times 10 to the negative 5. So let's do that. Negative log 1.76. Okay, and we get 4.75 for its pKa. Now, with that being said, though, what does that mean? Is especially when you're working with buffers, for example, if you're trying to set a buffer for acetic acid in this case, the pH would most likely fall somewhere in that range. It would be exactly around 4.75. That's usually what pKa is used for. in buffer solution, it kind of tells you what its, I guess, limits are, like where it would fall. It's also very good when you're using pH indicators, because based on the pK, you want to pick pH indicators that have a similar pKa value of what you're working with, because that way when there is a color change, it's a better representation of the actual base or acid being used up in that solution. Okay, so yeah, oh yeah, they use acetic acid as well. So yeah, it is just translated as you saw. pKa is like the pH, Ka is like the concentration of hydronium ions, and they're solved the same way. Okay, now question 18. So, what is a molar mass of fluorine? I'll fix that later. So, I'm actually going to pretend like they didn't tell us that it's I want this highlight. There we go. So molar mass of fluorine. I'm pretending they didn't tell us that you know, it's F2. So as I said, is fluorine gas, atomic element, molecular element, or molecular compound? It's only asking for fluorine, so we can definitely cross out that it's a molecular compound because it's only made up of fluorine. Now, atomic element versus molecular element. Fluorine is a gas that prefers in the environment to be F2, okay, in room temperature. So with this makes fluorine a molecular element. Okay, now knowing it's a molecular element, we can no longer just get the atomic mass unit. We need to do the same thing that we've been doing for the other questions. We need to find its constituents and multiply accordingly. Okay, so that's 18.998 times 2, 37.996. And then because that's the only thing we had to add, our molar mass of fluorine gas, F2, or just F2, it doesn't have to be a gas, but that's typically what it is in room temperature, is 37.996 grams per mole. So let's see what we have here. If they went through all these options, A, B, C, D, 9, 18, 19, 38, the only option that's close enough would be D. That is a molar mass of fluorine. So exactly, they use a periodic table. One fluorine weighs approximately 19, and it's a diatomic element, aka a molecular element. You need to solve it like that. All right, and now question 19. Okay, what is the chemical name of BaSO3? It's so I always get tempted to just read out the actual name. Chemical name of BaSO3. Okay. I always get confused back. I previewed this question, and they called Ba magnesium for some reason. But yes. So remember what we do? We separate by its constituents. Well, we're not trying to find molar mass, but we separate them nonetheless with the cation and anion. We have barium here. Okay, the 56 element, and we have some form of sulf something. Okay, so it's sulf. Okay, now remember sulfate ion is SO4 2 minus. That's a sulfate ion. So funny enough, to get to sulfate to get to SO3, it turns from 8 to ite. So this is a sulfite ion. The cool thing is though, actually, is that it actually does not affect the charge of it. It's still gonna be 2 minus. Why? I couldn't tell you. I'm gonna be real honest with you. But it is SO3 2 minus. And barium being the 56 elements, right? So, you know, if we wanted to do the whole electron configuration, we start at xenon, and we just have 6s2 because it's in the 6th row, letting us know that it only has 2 electrons in this valence shell. A lot easier to get rid of 2, so we have typically is barium 2 plus. So because these two already balance out, that's how we got BaSO3. Now we just put the names together. We no longer need the ion part, so really the name for this chemical is barium sulfite. That is the name for this. So let's see how we did. The cool thing is, though, if it was magnesium instead of barium, as they may have put here, it would still just be magnesium sulfite. So it wouldn't affect the equation so much. So exactly. Nice. Barium sulfite. So the 8s and the ites, like what I did here, this is something you have to memorize. It's always best to memorize the 8s first, because once you get comfortable with the 8s, the ite is just one less oxygen. So like if you had phosphate ion, so phosphate is PO4 3 minus. Phosphite is PO3 3 minus, if I remember correctly. Let me see. Because there's no point of saying that, and then it breaks the rule. Okay. So I don't know why they always throw in the hydrogen, but that's the key part. PO3 3 minus. There we go. PO3 3 minus phosphite. So let's move on, because we were able to get that question correct. On to question 20. What is the arrangement of the following compounds from highest to lowest boiling point? Arrange these from highest to lowest boiling point. Okay, so we have CH3OH, CH3Cl, and CH4. So in order to solve this, actually, we need to understand what so I guess we need to understand what each of these molecular compounds are composed of in terms of the type of bonds they have. Okay, because depending on the bonds, that's the amount of energy it takes to be able to break. The amount of energy it takes to break those bonds are different. So we have CH3OH, which looks like this. Okay, CH3Cl, and CH4. So let's actually start with what they all have. Okay, they all have, in each of these H's, they have non-polar covalent bonds. Okay, that's C to H. How do I know that? Just in case you're not familiar, when you go to the periodic table, it's based on the electronegativity difference. If it's less than 0.04, then it's a non-polar covalent bond. Electronegativity of carbon is 2.55, and hydrogen is 2.20, which is a difference of 0.35. hence how we have non-polar covalent bonds. Okay, now let's look at what the other difference of bond is. Okay, we have carbon to chlorine. Okay, 3.16 minus 2.55. That's 0.61. So we have a polar covalent bond. Okay, that's C to Cl. And now C to O, 3.44 minus 2.55 is also another version of a polar covalent bond. Okay, and now for the last one we have O to H. Okay, and oxygen to H, right? That one we can definitely write it as polar covalent bond, but you have to actually recognize it, because OH right here, this is actually a type of hydrogen bond. Okay, so the reason why I wrote it like that is because as we go down this list, it goes from lowest to highest energy. Okay, it's stored in them, as in the hardest ones to break are at the bottom. Non-polar covalent bonds, they can break apart relatively easily. So the higher the energy, the higher the boiling point is going to be, as in the higher the energy you need to break it apart. So now, based on this, right, the only one with the hydrogen bond is right here. Okay, meaning that to arrange these from highest to lowest boiling points, we would still have the CH3OH in the beginning, and then polar covalent bonds they require more energy to break than non-polar covalent bonds, which was identified here. Okay, meaning that now we have next CH3Cl, and then the last one would just be CH4. So that's from the highest to lowest. So going lowest boiling point. Okay, so it actually was already arranged for us, but this explains why. When you look at the bonds actually involved in them, hydrogen bond, very strong bond. Only thing that beats hydrogen bonds are actually ionic bonds, and then we have polar covalent bonds, and then a non-polar covalent bond. So the stronger the bond, the harder it is to break them. That's requiring more heat. So the order is ionic, yep, then hydrogen bonding, then dipole, and then van der Waals dispersion forces. Okay, so these will be considered like dipole, because these polar covalent forms do form dipoles. So this would be a dipole. Okay, and this right here would be more like the van der Waals, as in really most molecules you see will have that dispersion force. That's like the basic force that just everything has, and then you kind of just build from there. It's just like at least that relationship, right? So the number of carbons present to structures is directly proportional to the boiling point, but each one has only one. And then when you branch, branching is inversely proportional, so that means the more I guess if you compared this to this, same thing, but this would have a higher boiling point because it's more spread out than this one. This one would have the lower boiling point, as like a rough picture. But yes, that's what I mean by branching is inversely proportionally. As the more branching you have, as the more things you have that branch out from like the main chain, the lesser your boiling point would be, as long as you have the same amount of carbons. So you can't compare like different molecular. Actually, the best thing to just say is that we're talking specifically about structural isomers when we refer to this branching thing. So we have CH3OH. Methanol has hydrogen bonding, which is what we know. Chloromethane has a dipole-dipole interaction, and this one's just van der Waals on dispersion forces. So the order is CH3OH, yep, CH3Cl, and CH4. This is correct. And now, question 21. With that, another water break. What color of light has the highest frequency? Great question. So, what color of light has highest frequency? Okay, so for this type of question, actually, how do I put this? To find out which color of light has the highest frequency, you need to be familiar with the actual formula for it. So wavelength, okay, if I remember correctly, so how long the light is equal to c times f. Okay, the speed of light, okay, is equal to wavelength. No, wait, is this c times f? No, that's not it. It actually, this would be the formula. Frequency times wavelength is equal to the speed of light. Okay, so with that being said, c is 3.0 times 10 to the 8 meters per second. Okay, and the way it works is that frequency highlights actually, in a sense, how often it occurs, like per second. Hence how you can still multiply it and have because frequency, the units is actually s minus 1. But now, enough of that. The thing is, though, is that the relationship is pretty much that as wavelength goes up, because it still has to equal a constant of 3 times 10 to the negative 8, as wavelength goes up, frequency goes down. Okay, so you want to identify the light with the actual smallest wavelength so it can have the greatest frequency. So for this one, you kind of have to either memorize or literally look at a sheet. But remember the whole colors of the rainbow, Roy, G, B, Biv. Okay, so red, and this one is violet. Okay, the reason why it's actually organized like that, the reason actually when you see a rainbow, it's actually organized like that, is because of the fact that the longest wavelength, okay, is red. Red is the longest wavelength, and violet is the shortest wavelength. Okay, so because now actually we said that violet is the shortest wavelength, it means that of all these in these colors, violet has the largest, aka highest frequency. So when they ask this type of question, always think of the rainbow, and it's important to organize like this, because the way it appears on the rainbow is coincidentally actually matching with the length of the wavelength. Okay, so this is red, orange, yellow, green, blue, violet. Okay, and then you see like Roy G Biv with like indigo, but indigo is pretty much like a mixture of blue and violet, so just know it's kind of like in between. But point being that this is the order you definitely need to memorize, because exactly if they ask which one has a larger wavelength, yellow or green, you would say yellow, meaning that green is one of the higher frequency. So point being, for this question though, what color of light has the highest frequency? It's violet. Okay, so they do specify in terms of 430 trillion hertz to 750 trillion hertz. You can guess that the lowest one, that would be red, and it actually says right there, red. And when they refer to light, they mean visible light, not ultraviolet and things that go beyond that, because then at that point the frequency can just keep going on and on. Yeah. But in terms of light, they're meaning visible light, so colors, and this is correct. So with that being said, it was on the question 22. What is the lowest structure of phosphate? So when they even say phosphate, they would actually have to mean the phosphate ion. Structure of phosphate. Okay, so like I said, they would mean the phosphate ion, which is something that you do have to memorize as well, because if we were saying because I remember you have to memorize these, but phosphate is PO4 3 minus, right? And the math actually makes sense because if you actually go to the periodic table and you're doing the electron number, -2 -8 +5 +5, so we have in total 3 minus. But point being though is that if they said what is the Lewis structure of phosphorus tetraoxide, then we would have without the charge. But because they say phosphate, they're referring to a phosphate ion. Okay, so now that we've clarified that, it's PO4 3 minus. Okay, so how do we do this? We just kind of draw it out. We assume that phosphate is going to be in the middle because the only one, and it's going to be sharing with 4 oxygens. And just as a disclaimer, phosphate is just one of those that does not care about the octet rule. So you're going to get quite a weird looking answer. Okay, so with that being said, oxygen has 6 electrons. In fact, that's what I forgot to do. Actually see how many electrons we're dealing with. So phosphorus is on the 15th column, so it likes to have 5 electrons. Oxygen is on the 16th column, so it likes to have 6, so times 4. Okay, and we have 3 extra here, so 5 plus 3 plus 6 times 4. In total, we're dealing with 32 electrons. Okay, and as a quick review, because we're always doing this, phosphorus, okay, if you want to do in terms of the electron configuration, we start at neon and then be 2s2 2p3, which does account for the 5 valence it has. And oxygen, I'm sure you're getting tired of these, but I'm going to keep doing them until you are an expert. And it's going to be, whoops, not 2, sorry about that, it's going to be 3s2 3p6. See, not yet an expert. Okay, 3p3. And oxygen is going to be 2s2 2p4, hence how you have here 6 electrons. So 32 total though. Back to our actual problem. Oxygen is sharing 1, so it needs to account for the other 5. So 1 2 3 4 5 6. Same here. 2 3 4 5 6. 2 3 4 5 6. 2 3 4 5 6. So now phosphorus is now, of the 5 electrons it has, it's sharing 4, so it's going to have an extra one kind of like right there. Okay, so with that being said, it's going to pick 1 oxygen and make it a double bond. So technically, yes, this is going to also have resonance structure, because it could have been any one of these oxygens and this would have worked as well. So yeah, that's a thing. Yes, phosphorus phosphate ions also have resonance structure, and this one will be a nightmare to draw either way, because you have to draw this one 3 more times pretty much. But these oxygens now, that extra 3 electrons right there, and right there. Okay, so with that being said, this phosphate ion, breaking the octet rule, has a double bond here with one of the oxygens and single bonds with the rest of them. Okay, and the oxygens out here are all filled up and this one has just 2. So if we actually did the quick electron number for phosphate, it'd be 5 minus, as you see here, it has 0, but it's sharing 10 of them, so it does equal 0, so that's good. Oxygen, the one on the right here, is going to be 6 minus, it has 4 to itself, and it's sharing 4, so that also equals 0. But then these 3 oxygens to the side, you will see that that's where the negativity is. It's going to be 6 plus 2 over 2 equals minus 1. So exactly, each of these oxygens out here would be where the negative charge is now. Hence how we have PO4 3 minus. Now, if we wanted to resonance this out, it would look something like this. Okay, starting with a single bond. Jesus. Yeah, I don't know how to do this one as a resonance structure, because this double bond here, okay, will be jumping into any of them it so chooses to. So unless I do it as like a 3D structure, there's really no way for me to actually like convey this properly. But exactly, the one thing we can say though is that this answer here would have 3 other structures, because that's where the double bond would move each time. Okay, so exactly, the negative, actually I can keep that there then. Okay, where are the other ones? There we go. There we go. So this would be the structure for it, the Lewis structure. But like I said, it would have 3 other structures. So I'm going to just draw them in terms of the molecular structure, so I don't have to work too hard at them. But you would have this as well. You would have this as well. And you would have this as well for its resonance structures. So yeah, that is the answer to this question here, Lewis structure. And yep, 1 double bond and 3 on the side, and yep, that is correct. And as I said, there's resonating, there's resonance, but doing that is gonna be something else. So yeah, with that, let's move on to question 23. Molar mass of sodium hydroxide. So with that being said, sodium hydroxide, you first have to figure out what molecule it is. We have sodium, and this part you have to memorize, unfortunately. Hydroxide is a type of ion that's just OH minus, hence a hydro and oxide. But that's it's a name you have to just really get familiar with. So that's sodium hydroxide, right? Now sodium, once again, it is on the first column, so you can say it's most likely just 1 electron. But if we drew it out, okay, it would be neon 3s1. Okay, oops, that's strange. Oops. Yeah, okay, well, we're gonna just redo that. 3s1. What's going on? Interesting, my highlighter is not working. There we go. That was weird. 3s1. Okay, there. 1 lone pair, meaning that, not 1 lone pair. 1 electron is valence shell, meaning that sodium to get to an octet, well, quote unquote noble gas, is just plus. So sodium hydroxide is just, because they already cancel each other out, NaOH. So we're gonna have 1 Na plus 1 O plus 1 H. Okay, so that's 22.990, 15.999, and 1.008. So plus 1.008, we get 39.997 grams per mole for sodium hydroxide. Okay, and they say, yeah, 40 grams. They don't really discuss on how you know, but exactly, because it's one of the things, unfortunately, hydroxide, I would say that one really memorize, because you also see it in acid and basic solutions. You have to be able to recognize what a hydroxide is. Okay? And yes, actually, in regards to acid and bases, sodium hydroxide is what you consider a strong base. And now question 24. Okay, we have, what is the Lewis structure? I mean, I wish it wasn't so big. For CO3, for carbon trioxide, CO3, something you don't see often, but it can exist. I'm really actually hoping that they did not mean carbonate, because we will find out if CO3 is something that's possible, but we're gonna work through it nonetheless. So CO3, okay, carbon, you love to see this. We're gonna do the typical we're gonna do what we always do, electron configuration, 2s2 2p4 2p2, sorry, that is carbon, oxygen, once again, 2s2 2p4 now, exactly, there we go. Don't know why it's doing that, but exactly, point being though is that now we know that there's 4 electrons carbon can work with, and 6 electrons oxygen can work with. So that's 4, 6 times 3. So that's going to be 18 plus 4, 22 electrons. Okay. So let's see if this is possible, because if they mean because they didn't put any charge with it, but if they meant to put CO3 2 minus, the carbonate ion, then that would probably be a lot easier to work with. But let's just try solving it first, like carbon trioxide. So let's see here. We have carbon in the middle. Okay, it's going to share 2, 3. Okay, carbon trioxide. And now oxygen still has 1, 2, 3, 4, 5 more that it wants. 1, 2, 3, 4, 5 more that it wants. And 1, 2, 3, 4, 5. Okay, and carbon is right now sharing 3. So just 1 more. Okay. So you can already see there's going to be quite an issue here, because it can only work with one of them to form that double bond, but the other oxygens just will not be yeah, exactly, this becomes almost an incomplete structure. So you do need the ions here to be able to fill out the rest, because that's the only way this oxygen gets filled and this oxygen gets filled, because the oxygens wouldn't bond to themselves. Like, we make like you would never send like this in elements like that. That wouldn't work. I mean, actually you could. Sorry about that. I'm thinking of like, this does count as a shape you can see when they form rings, so you could see that. Sorry, but point being, in terms of here, the oxygens will not bond like that, is what I'm trying to say. Okay, so with that being said, okay, I'm gonna assume they meant carbon. So this is carbonate ion. I want to assume they meant carbonate ion, okay? Because then we have this, okay? So it's no longer carbon trioxide. And that one, as you can see, that's why we don't see carbon trioxide in the ecosystem, because it's a very unstable looking molecule. So with that being said, let's now solve for the carbonate ion. Okay, and once again we have our lovely resonance structure, which like I said, trying to show it with the dashed lines becomes not fun. But exactly, we still have to make sure that we actually did this correctly by counting the number of electrons. So we want, now that we've added the 2 minus, it's going to be 24 electrons we're working with. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So perfect. And the electron number for carbon, that's 4 minus. It doesn't have any, but it's sharing 8 of them. Exactly. The oxygen on the right is 6 minus, same as we did before, 4 plus 4 over 2 because of a double bond. That's 0 as well. And the 2 oxygens now at the bottom, that's where the negative charge is going to be, as you can see. 6 minus 6 plus 2 over 2 minus 1. So exactly, the negative charge is going to be on each oxygen there. And this is going to be our lowest structure for a carbonate ion, because carbon trioxide, I just don't see how you can draw that without forming a very strange bond or adding more electrons like we did to get the carbonate ion. So with that all being said, the other resonance structures are going to look kind of like this, where now double bond is here, okay, or double bond is here, okay, and exactly that's where this is where the negatives are, and here these are where the negatives are. So yeah, these are the other resonance structures for the carbonate ion. Now let's go back to this 22 valence electrons, lowest structure. This exactly doesn't even satisfy the octet rule, so you need it to be a charge, and so it is solving for the carbonate ion, because as I said, this doesn't work. Carbon, oxygen, all the rest, they're just unsatisfied. So exactly, that's why we have the carbonate ion. Carbonate, sorry. Carbonate would be like CO2, 2 minus. Let me actually see if that exists. I know we have carbon dioxide, but if we have carbonate, it would be now with the charge. Yep, CO2, 2 minus. So carbonate is definitely a real thing. But this is carbonate ion. So question 25 now. Okay, what are the isomers of C6H14? That's a very loaded question. We can't really have a constitutional isomer. We can have structural isomers, because they can have like the carbons set up in different parts. But in terms of constitutional isomers, in terms of when dealing with chirality, because we only have hydrogens bonded, there's no way you can twist the same molecule to be able to get something different, because all the hydrogens are the same. But when we're looking at structural isomers, which is the same name with different structure, we can have that, which would just be hexane. We could have this, sorry, okay, which would be 2-methylpentane. Okay, you could have this, which is 3-methylpentane, and then if it went back here, it would back to be 2-methylpentane, because this would be 1, 2, 3, 4, 5, exactly. So 2-methylpentane, I'm just going to add it here. You can also have 3-methylpentane. You can also have, oops, I guess you can't, because as soon as you do that, you're back to, how else can you reorganize this? That's a great question. Oh yeah, whoops, I'm thinking too. You can have this, okay? And this would just be, trying to think if there's anything else we can do with this. Nope. This would be 1, 2, 3, 4. It'd be 2,3-dimethyl 2,3-dimethyl butane. These are all isomers of C6H14. You're probably wondering, like, oh, we can't do like a ring, because once you have a ring, that would actually be C6H12, as in now you've lost 2 hydrogens. So no rings. It still has to be in its as, I guess, there's no, the carbons can't attach to each other is what I'm trying to say, but you can have it to where you can move certain bonds. Like, you cannot have a closed system, but you can move certain bonds around to where there's still going to be the same amount of hydrogens. So if I were to count, actually, you see 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So yes, all of these here are C6 H14. Shoot, I was afraid that's gonna happen. So we're gonna leave the rest. But point being, these are all the ones I can think of that are isomers of C6H14. There may be more, but I do believe this might be it, because no matter how else you rearrange it, you end up with one of these names. I tried putting in terms of like you know, it, like, even if I did something like this, it would still end up being like the 1, 2, 3, 4, 5. It'll still be 3-methylpentane. So yeah, I believe these are all of them that can exist. Okay, so yeah, structural isomers, like I said, because they're all C6H14. We don't count like the whole stereochemistry, because exactly, they're all hydrogens on that carbon's attached to, so it would not have like different types of constitutional isomers. Okay. Oh, there's a different type you can do. I didn't think about that one. So exactly. So we had hexane, 2-methylpentane, 3-methylpentane, 2,3-dimethylbutane. But I never thought about that though, where they're actually on the same end. So if I did that, right? Like that. That's the one I was missing, which would be 2,2-dimethylbutane. So we're almost there, but exactly, I was missing that one because technically we can move this bond over to that side. Hence how they got 2,2-dimethylbutane. So we had 4 out of 5. Definitely a good attempt, but this is correct. And exactly, as you notice, there's no rings here because exactly you still want C6H14. Okay, so now question 26. Is water polar or non-polar? So first we need to actually draw the Lewis dot diagram of water. Okay, I guess there's 2 ways to do this, but I feel like this would be the best way to see it. H, we just can't skip too far. H2O. Favorite thing to do, hydrogen is just 1s1, oxygen is still helium, 2s2, 2p4 to make 6 in total. So we have 2 hydrogens, 1 oxygen, so that's 6 and 2, so that's 8 electrons total. Okay, so with that being said, because that's 8 electrons total, okay, when you draw it, oxygen's in the middle, hydrogens, they're each sharing 1, so they're done. Oxygen still has, because it's sharing 2, it still has 4 more unaccounted for. So 1, 2, 3, 4. So that should actually give you a big hint of whether it's polar or non-polar. You have 2 lone pairs. Now you may see this picture and think, oh yeah, then that makes it non-polar. Let's actually draw it what it looks like in terms of its shape. And to find that out, actually, oxygen has 4 electron pairs. As we discussed, because 2 bonds and 2 bonds and 2 lone pairs. So oxygen has 4 electron pairs. And that is a tetrahedral, actually. So that's what the electron pair geometry. So electron geometry, but it has 2 bonds and 2 lone pairs. So its molecular geometry is called bent. Okay, the reason why it's called bent is because it looks like this. Whoops. Okay. Alright, and because it's like that, water actually has a directionality this way, where the lone pairs are pointing, okay? Because that would be the molecular geometry of it. So water, because of that, those lone pairs, this is a polar molecule, okay? You have the slightly positive charge of the hydrogens and the slightly negative charge at the oxygen, and exactly, it's pulling everything with the lone pairs in a certain direction, okay? And you can actually see the Vesper here. Oxygen is this one here, 2,2, tetrahedral, like I said, and bent. This is what water looks like, and it is polar. So water is polar, and this is correct. Okay. So with that being said, we're on to the next question. Question 27. What is the geometric name of H2CO2? Okay. I think I know what they're asking for here. I think they're asking for what we just actually did, the electron geometry and molecular geometry for H2CO2. And molecular geometry. We can only find that out by, once again, starting with the lovely Lewis dot diagram. So for that, hydrogen we know is 1s1 for electron configuration. For electron configuration. Carbon is starting at helium, 2s2, 2p2. Oxygen starting at helium as well, 2s2, 2p4. So with that being said, carbon has 4 valence, hydrogen has 1, oxygen has 6. So that's 1 times 2, 4, and 6 times 2. So that's 12 plus 2 plus 4 should be 18, but I'm just going to check. Okay, good. We have 18 electrons total. So first, let's actually find out what this H2CO2 is. So CO2, right, as discussed, the ion, 2-, is not carbon dioxide, okay? This is, as you remember, carbonate was CO3 2 minus. CO2 2 minus is carbonate. So this is where it gets tricky, okay? Carbonate turned into an acid is carbonic acid. Okay? Carbonate turned into an acid is carbonous acid. Let's just find out if we're correct, because I don't want to be saying something wrong. Okay, I believe it's now, instead of ick, it's os. Carbonous acid. CH2O2. Whew, that's nice. That's very nice. Carbon. So exactly, it goes from ate to ick, and from ite to us. OUS. So carbonous acid. So that is a name, okay? If they're asking for, when they're asking the question, the name of the compound, it is carbonous acid. Now to figure out the electron and molecular geometry, we have C, okay, in the middle, or we don't 18 electrons. We have H, O, okay. Actually, that's just an assumption. Let's actually do the CO2 first, because you would actually see, based on that, where the hydrogen would actually prefer to go. Ooh, tricky. So we have CO2 2 minus. And remember, CO2 2 minus, okay, that one also has 4 plus 6. There's 4 here, 6 times 2. So it's still going to be 12 plus 4 plus 2 more. It's still going to be 18 that it wants to account for. Because when hydrogens come in, you know, it wants to quote unquote fill in that extra space as a proton only, so it doesn't bring any of its own electrons. But with that being said, let's solve for it. So oxygen has 1, 2, 3, 4, 5 more. 1, 2, 3, 4, 5, and carbon is sharing 2, so it needs 1, 2. Okay. So with that being said, to be able to balance this out, CO2 2 minus, this is where it gets tricky. Because if we do the double bonds, it's just carbon dioxide. So there has to be a way to move things around. Ooh, this is where it gets tricky. H2CO2. I'm beat. I'm genuinely beat. Because right now we have 1, 2, 3. So wait, 2, 4, 6, 8, 10, 12, 13, 14, 15, 16. So we have 16 right now. So technically this would be what CO2 started at, and exactly what you get if you do a double bond there. Maybe actually, if we filled it in, if we did remove one here, okay, so double bond there, right? And to add, okay, I see. I think I see now. This here and this here, okay? So with that being said, we have now C O O okay, because this is now going to be completely filled. Okay, so with that being said, yep, this kind of makes sense, because I don't know how to reorganize this without breaking the octet rule. So we have now when we count 2, 4, 6, 8, 10, 12, 14, 16, 18, right? So with that being said, if we did the whole math, just the electron number, carbon would be 4 minus, it has 1 lone pair, so 2, but it's sharing 6/2. Oh, is that correct? 18. Interesting, because I definitely added 2 electrons, because carbon is still 4. No, something's not right here, because 18 electrons total, because for CO2 minus, right? And we have 2, 4, 6, 8, 10, 12, 14, 16, 18. What am I missing here? So 2 and a lone pair, and it's sharing 6. Oh wow, I'm blind. My math is wrong. That's 2 plus 3. That is -1. Oh, thank God. Oxygen. So that's 6 minus. Wow. Okay. 6 minus 4 plus 4/2. That is 0. And then 6 minus 6 plus 2/2. That's -1. So the only way it makes sense actually is when the negatives are here. Okay. 1 carbon is negative and 1 oxygen is negative. Okay. So with that being said, the place the hydrogens would go actually for H2CO2 would actually be to, in a sense, make no longer have that negative charge. This is what we'd have. Those are where the H's would go. Okay, surprisingly not on each end. So carbonous acid technically could only get rid of 1 proton, which is the one attached to the oxygen. We'll discuss more of that later. Point being is that the electron and molecular geometry for this, okay, it will look kind of like this. Oops, sorry, wrong one. Okay. Okay, that's really the only way it works. Okay, and actually that's actually makes sense because this is what we want actually in terms of that for acids. When you notice in terms of when it comes to what's it called, hydrocarbons usually have this OH type of structure. It just happens so close, which made it look so unfamiliar. But exactly, this is what you'd have. Okay, so it's just a little upside down. Okay, so I'll actually redraw that. Okay, the carbon is satisfied, oxygen is satisfied, everyone's satisfied. This would be it. So now we're referring to the shape of the carbon. So we have only 3 electron pairs. Okay, so this is going to be trigonal planar. And there's also no lone pairs, so that's going to be its shape, trigonal planar. And we can even check with the Vesper theory. Exactly 3, 0. It's going to AX3 is going to look kind of like that. It's going to be flat with the oxygen doing its bad stuff at the end. So, formic acid is what it's called. Interesting. I wish someone would have told me that, because that was the most stressful thing I've ever done. But yeah, so formic acid, which is also carbonous acid, okay, and it's also known as methanoic acid. So we were on a whole different wavelength, people. But that's okay. The point being, though, is that once I saw like that, I was like, I recognize that is exactly methane because it has 1 carbon. So methanoic acid is also a viable name, and it is trigonal planar, exactly, because hybridization 3, so it is sp2. And yeah, so at least we got the trigonal planar part right. Finding Lewis structure was the most frustrating thing ever, but you know what? I'm actually proud because we were able to actually show why it's not the hydrogens on each oxygen, but rather there's a hydrogen on the carbon and a hydrogen on the other oxygen. So, you know what? That's small victories, you know? We solved it in an unorthodox way, but we still got the answer. How do you determine the pH of citric acid? Okay? You just go to our periodic table. I'm kidding. pH of citric acid. So for this, first thing you need to know is whether it's a strong or weak acid. Is it weak or strong acid? Okay, because I know we've gone over this question quite a few times, so I'm kind of just gonna get the gist of it. You use the Ka to find out if it's strong or weak acid. As we discussed earlier, Ka greater than 1 is strong. Ka between 0 and 1 is weak. So we look at our sheet, citric acid. They really have to give you the Ka value from this if they want to make you find the pH. They would never just say, what's the pH of this solution, and not tell you any information about it, because you do need the dissociation constant. So citric acid. What do you mean citric 1 and citric 2? Oh, I see. So this would be the OG, or the original citric acid, where it has not yet lost any electrons just yet. So even the greatest citric acid is sitting at 8.4 times 10 to the negative 4, making this citric acid a weak acid, okay? And because this is a weak acid, there's things you need. You need to first make sure you have the right, equation. So you would have C6, right? So C6H7. Yeah, you see, I'm not gonna do that. Okay, I'm just gonna write down what they have. H3C6H5O7. Okay, that's citric acid. Okay, so that plus water. Okay, because it's only getting rid of just one electron. Okay, so aqueous. We have now, it's because of weak acid, we have to use this special arrow. Okay, and we have H2C6H5O7 aqueous. It lost one electron, it's going to be minus, plus H3O plus. In fact, we can just shorten down to just where it says HA, and this would be the A minus, and this would be the H3O. Because those are the things you need, actually, because they do have to tell you as well, not only the Ka value for citric acid, but also the concentration that you started out with, which is what we have in terms of the HA. Because for that, you need the ICE table, okay, which stands for initial change equilibrium. And you would pretty much have your concentrations of each one. And you know that for the A minus and H3O, you have to start with 0 because there's nothing there at first, okay? So the HA would have a big value like, let's make it X, okay? Like a big X. In fact, let's make it D, okay? All right. So now, the way this will work is that the change that for every one it loses, 1-to-1 ratio, for every one it loses, right? These ones gain that same amount, and then we have in total is just going to be X D minus X. So I will always say this as a review, okay? If the concentration, okay, if D is equal to 1,000 times Ka, not equal to, greater than, okay, then the change in x, okay, will be so small is that so that d minus x would really just equal d. If the concentration is not greater than 1,000 times the Ka, the change between d minus x is great enough to where you have to factor them in. The reason why I say that is because the formula you're working with in total to find even the concentration of acid you have in there is Ka is equal to products, okay, which includes the concentration, over reactants, which does not include water because water is just like the solution, right? So if we plugged everything in, right, if the concentration was 1,000 times greater than Ka or more, okay, you pretty much would have x squared, because that's the only x's, over d. That's what you do, and so you just make it d times Ka, and that would equal x squared. So then you square root both sides, so that means x, which is going to be the concentration of your acid, is the square root of the concentration d times Ka. Now, if you had it to where it was less, unfortunately this would call for the quadratic formula. Okay, you'd have x squared over d minus x, so that'd be Ka d minus Kax is equal to x squared. So x squared plus Kax is equal, minus Kad is equal to 0. And then use your quadratic formula, you know, the ax squared plus bx plus c, with b is equal to 0. And then you have to do the whole square b plus or minus b, I'm really rushing through this, sorry. So it'll be minus b plus or minus b squared minus 4ac over 2a. Knowing the values that we have there, okay, if we simplify this, we would have it to where it's minus Ka. Kind of circle this thing. There we go. It'll be minus Ka plus or minus the square root of Ka squared. It's going to be now plus because the last part is minus Kad, right? So it'll be plus 1, because in this case A is 1, C is Kad, so 1 times that, so Ka squared plus Kad, okay? Right? And then the whole thing will be divided by 2. This would be what you use to find x. You would get a positive and a negative value. Ignore the negative value because you cannot put in something and get more of the something you put in, if that makes sense. The reactant has to break apart. You would not form more reactant when there's nothing to use to even form more, okay? So you'd only take the positive number of it, of the two answers. So now that we've done all of that, that x is going to be our concentration of H3O as established all the way over here, okay? And then finally we can use this formula, okay? pH is equal to negative log H3O. So as you can see, two paths lead to the same answer though, okay, of finding at least your concentration of H3O. The important thing to know is that exactly this relationship here. If it's greater, save yourself some work. If it's not greater, good luck. I personally don't like using quadratic formula, but it is always going to be the most accurate answer. So even if you're unsure about the relationship, please use the quadratic formula because you will get the most accurate answer. Okay? So that's all the steps you use to find the pH of citric acid. So I would say this is incorrect because this doesn't really answer the question. But funny enough, if we were to, let's see, 50 grams per liter, right? Oh yeah, then I have to find out the whole mass. Actually, I'm gonna search it up. Molar mass citric acid. because right now I don't want to have to waste time showing you the math calculations for it. So citric acid is 192.124 grams per mole. So here, when they said 50 grams, it's actually, so 50 divided by 192.124, that's about 0.26 moles per liter. So exactly, now we have our concentration, it's 0.26. Alright, if we just use a quadratic equation right here, and using that citric acid, okay, we would have, okay, so Ka of citric acid is 8.4 times 10 to the negative 4. So that's negative 8.4 E times 10 to the negative 4. I'm going to first do plus, okay, the square root of 8.4 times 10 to the negative 4 squared plus Ka times D. So that's, we said it was 0.26. So plus that times 8.4 E negative 4. Okay. And then just all that divided by 2. Okay. We get 0.006. Okay. And then we're going to also do the opposite way as well to make sure that one answer is negative, one answer is positive. So let me just actually check if I did this correctly. Oh, whoops. I did not. Gotta make sure that the divided by 2 is at the end. Okay. Okay. So first, let's get that 0.26. That's frustrating. I just want to get. Okay. So if we did 0.26, okay, and then we did the actual. Okay, so we get 0.069, right? That is our X value when they mentioned that concentration. I'm just gonna write it down so I don't forget. 0.0698. Okay. So now to check if that's the only answer we get, when we do the minus version, we get negative 0.017. So that one we ignore. So using that 0.698, we're gonna do the negative log of that. We get 2.15 as a pH. Funny enough, this is correct. Its pH is around 2 to 3, but still, this is incorrect because they really missed out on every step you need to take to actually be able to solve it. So that was question 28. Let's just go for the last few, okay? Because I only had 2 more questions to solve, and I would like to finish them. So just try to blast through them, while still understanding it. I feel like we did this question. The electron configuration of selenium beyond its normal gas? Oh. It may have been something else. But selenium, if you go to the periodic table. No, this is unfortunately the same question. So, well, and our periodic table decided to crash on us. Well, we remember this one. Okay, selenium started. So selenium electron config beyond noble gas. Okay, so with that being said, we have just again the argon, and if our periodic table loaded, there we go, selenium all the way over here. I think it was something else. No, it might have been this. It's gonna be first. We know it's gonna be 3D10 first because it's gonna go through the whole D roll, and then 4S2, 4P4. Yeah, so it is C. Yeah, we've definitely done this question. For those that may just be joining in, we did this question earlier. I believe that was question like 2 or something. It was quite early in the presentation, but yeah, you can definitely check that out. So I'm not gonna take time on that. I'm just gonna see what the last question is like and see if we can solve it in like the next few minutes. I do like to end with at least 30 questions a session. So that oxygen one was, oh wow, nice. Meaning of Ka in chemistry. Really though, that answer is correct. Ka is dissociation of acid constant. That's really all you need to know about Ka. To explain further though, what that means though is that if you put an acid in solution, Ka is a representation of how much that acid will separate into its cation and anion. That's it. I wish there was more I could add with it, but like we've been stating in earlier questions, Ka greater than 1 is a strong acid. Why? Because that is saying that if you threw it into water, it would separate completely. There would be nothing left of the original acid. It will separate just into the cation and anion. A Ka less than 1 but greater than 0 is a weak acid, because you throw it in and it'll kind of like dissociate a little bit. It'll have pieces of it, but there'll still be that original acid still left in the solution, which is why, as you notice, weak acids usually have a higher pH than strong acids, even if they're the same concentrations, because less of it dissociated, meaning that you have less hydronium ions in the solution. So this is correct. That's really what you have to base it off of. And so this is your best friend, really, this sheet, because this explains why you can see in the Ka why these will all be considered weak acids and why these are considered strong acids up here, the hydroiodic to nitric acid are like considered the strong ones. So with that, this is correct. And also with that, just want to thank you again for joining me this session. Hope you have a wonderful rest of your day. Enjoy your Sunday. Get ready for the week. And with that, if you have any other further questions, definitely check the links in the description below. We're always here to help. You can even find some tutors. So yeah, have a great day, and